Hello everyone. Once again, welcome back to this course on discrete mathematics. And now we are going to a new series of lectures on mathematical induction. Before we go on to the actual induction, in this part 1 we are going to talk about sequence. Yes, there are a lot of sequences that you find in nature. Let's define what is a sequence, and then let's examine further on various sequences. Sequence by definition is an ordered list of elements. Now you know what are the elements, what is a set, what is a functions, and now you can have a sense of what is an ordered list of elements. Well, it's just like a set, but the elements can be duplicated. As you know, in sets it doesn't make any sense when you duplicate an element, whereas in a sequence it is possible that it can have elements that are duplicated. And elements are ordered. Unlike sets, yes, elements in a sequence has an order. Well, the term sequence itself gives us a thought on the order in which they appear. Let's say a sequence is a function from a subset of Z, an integer, to a set S. Okay, with this thought, let's say usually from the positive or negative integers. So say an is an image of n, a sub n is the image of n. So an, that is a sub n, is a term in the sequence. As we talk about sequence, let's define the sequence and let's see how we denote a sequence and what are the notions that have been used. So that's why this place where I am explaining about this an part. So here, if a sub n, we have this in the braces, means the entire sequence that enclosed. Yes, an, that is a sub n, is a term in a sequence, as we have seen, is the same notion as set as we have seen within the braces. Let's see some examples of sequence. A sub n equals 3 times n, or 3n. So what shall we expect from here? Yes, the term sequence here is a1, a sub 1, a sub 2, a sub 3, and so on. So as you replace n with 1, 2, 3, what happens? You have a sequence of 3, 6, 9, 12, and so on. So here the sequence a sub n in the braces enclosed of these numbers, plainly the multiples of 3, and it goes on because we have termed it as an integers. B sub n equals 2 power n. So what do you expect here? The same way, b sub 1, b sub 2, b sub 3, so on. Whenever the n takes the value 1, 2, 3, and so on, it changes, like 2, 4, 8, 16, 32. That is 2 power 1, 2 power 2, 2 power 3, 2 power 4, 2 power 5, and so on. So you can see here the sequence are indexed from 1. And at times in some textbook or some mathematicians might start a sequence with index from 0, but specifically here, as we have seen, we are starting a sequence with index from 1. That's what I said. Not all textbooks use this method. Geometric versus arithmetic sequence, and these are some of the fundamental sequences that you might have studied in your high school again. Let's brush up and review those sequences. So let's see how this sequence of geometric and arithmetic sequence grow. They are basically an arithmetic sequence increased by a constant amount. How is that? say we have already seen an example in which a sub n equals 3 n, that is 3 times n. So this constant amount here is 3. So with this 3 it increases, or the sequence grows with this constant amount. We know that it goes like 3, 6, 9 and so on. So that's an arithmetic sequence. How about a geometric sequence? So just have a thought on arithmetic sequence. This form is quite easy for us to understand. F of x, if you take it as a function, f of x equals dx plus a. As we have seen earlier, each number is 3 more than the last number, so that's it. Dx plus a, that's constant term, has been added to it again and again. That's for the arithmetic sequence. You can have the same line of thought for the geometric sequence, whereas in geometric sequence the order in which it increases as a constant factor. So we have seen this b sub n equals 2 power n, where you got the sequence 2, 4, 8, 16, 32, and you can see here that each number is twice the previous number. In other words, f of x equals a or power x. Yes, as you put the value for x to be 1, 2, 3 and so on, you get this sequence growing. Yes, that's geometric sequence. Let's go further down and see various other sequences that are available, and this is an interesting sequence, a Fibonacci sequence. Well, you might have heard about this sequence, and it has a unique feature in the nature. So for example, for a Fibonacci sequence, the first two terms are 1. So here f sub n equals f sub n minus 1 plus f sub n minus 2. You could say as f of n equals f of n minus 1 plus f of n minus 2. So these are the terms, the previous two terms being added to form the current term. F of n is the current term, and f of n minus 1 is the previous term, f of n minus 2 is the previous term. So each term is the sum of the previous two terms. That's what I meant. So here is a sequence we have seen in the Fibonacci definition. That's 1, 1, that are first two terms, and after that you have the sequence where you're adding up the previous two terms. So that is 2, 3, 5, 8, 13, 21, 34, 55 and so on. Well, as you know about this sequence, is called the Fibonacci sequence. We have this unique formula that defines this sequence. F of n equals 1 plus root 5 the whole power n minus 1 minus root 5 the whole power n divided by root 5 times 2 power n. Well, we are not going to derive this formula or going to examine this further, but we will see about the sequence itself. Well, this sequence is very unique, as I told you before, because it appears in the nature. So this is a shell, and you can see the cones of this shell, the crown, and then each layer has different steps, and it has a horn in each layer, and this horn again grows by means of the term 1, 2, 3, 5, 8, 30 and so on. So that's quite unique. Not only this, if you look back and see various other things in the nature, for example, how the petals in a flower is arranged, or for example, if you just look back into different dimensions that forms in a turtle's shell, you could find a Fibonacci sequence. Not only there are a lot of other places you can look around this Fibonacci sequence. Why don't you take some time and examine about this Fibonacci sequence? Just try to search for it. You will find there are a lot of things in nature that falls by this Fibonacci sequence. Let's see here a scenario where you have one pair of rabbits on an island, and this scenario is like the reproduction of the rabbits. Rabbits repeat the following two steps. It gets pregnant one month, give birth to another pair the next month. So what happens? This process repeated indefinitely, assuming that no deaths happen. So the rabbit gets pregnant the month they are born. Let's see here. So the question is, how many rabbits are there after 10 months? So first month you have one pair of rabbits. These are the original pairs. And what happens to these rabbits? Yeah, now the second month, the first pair of rabbit, the original one, gets pregnant. So third month we have two pairs, the child pair which is pregnant and the parent pairs which are recovering. How about the third month? Third month you have the grandchildren, that is children from the baby pair that is now pregnant, and the child pair now recovering, and the parent pair who are supposed to be the grandparents of the grandchildren there, now they got pregnant as well. So now there is two pregnant here. So then the fifth month you have both grandchildren and the parents reproduce. Three pairs are pregnant, the child, the two newborn rabbits. So this goes on. So 6 months, 3 new rabbit pairs are pregnant, as well as those not pregnant the last month. So you have 2 there. And the 7th month it goes on like 13 pairs, 8th month 21 pairs, 9th month 34 pairs, 10th month 55. So is there any unique thing about this? Well, note the sequence. You have 1, 1, 2, 3, 5, 8, 13, 21, 34 and 55. And there is one more thing about this whole sequence. As you see here, the 10th month, that is the 10th number, is 55 in this sequence. That's in fact, if you add 1 to 10, you get that number 55. Yes, this Fibonacci sequence is quite unique, and in this rhetorical scenario you can see how this sequence develops. So there is another application where you can think of this Fibonacci sequence, and if you have time, I would like you to examine more on this Fibonacci sequence, try to browse through the webs and try to find more information. Say for example, here is a kind of rectangular shape structure, and as you divide these structures evenly, like 1, 1, 2, 3, 5, 8, as you can see, each square contributes there to form this whole rectangle, and they in fact can give us some thought on how the things got used to it. So this kind of spiral things can also be found in the shells. Not only shells, even the way in which our universe spins around. Isn't it amazing to see how a small sequence, a small thing here can affect the whole universal structure? Well, talking about this universal structure, there is something else that you can think about. As you go on with this thing, like for example, you have the sequence like 3, 5, 8, 13, 21 and so on. If you take the ratio of these numbers, that can reveal you something else. So as you can see here, as the term increases, the ratio between the successive term approaches to 1.618. Initially the ratio was not that, but as you increase the term, it reaches to 1.618, and this ratio is quite unique. It's kind of a perfect ratio, and this formulae can also give us the ratio that has been approached, that is 1.618933989 and so on, it goes there. So we call this ratio as the golden ratio, and again this ratio can be found in the nature. For example, the ratio of human leg length to the arm length, the ratio of successive layers in a conch shell. Yes, that's thing that you found in the nature. Well, I recommend you to examine more on this golden ratio. As you can see, this golden ratio can be found in the nature, just as you can see the ratio between the legs and the arms. Not only that, there is some hint that you have find from the nature that is been bound by means of this Fibonacci sequence, and eventually we explored this golden ratio that ties them up. Well, now you can see how these sequences are quite important element of our discussion on mathematical induction. We will see more on this. Determining the sequence formula. So how do we determine a formula for any given sequence? So for example, you are given a value in a sequence. How do we determine the formula? Well, there are few steps to consider. For example, is it an arithmetic progression? In other words, is there a constant amount of term that has been added from the last term that you have in hand? Or is it a geometric progression? Each term, a factor of previous term is being added. Or is there any other relationship that you can develop in forming a sequence? Let's see. Does a sequence repeat itself? Does the sequence combine previous terms? Or all, you can see here, are there runs of same values? Is it coming out with the same values? Let's see here, there are a few sequences. As you can see, 1 0 1 1 0 0 1 1 1 0 0 0 1. Can you see what is happening here? Yes, right. You had 1 0, then 1 1 0 0, then 1 1 1 0 0 0. Yes, there is a sequence. The sequence alternate ones and zeros and increasing the number of ones and 0 each time. Initially the 1 was only one time, 1 and 0, then 1 and 0 appeared 2 times, then 1 and 0 appeared 3 times. Yes, you got the link. How about this one? 1 2 2 3 4 4 5 6 6. So do you see that the odd numbers just appear once and the even number repeats 2 times? Yes, that's a hint that you have. Likewise, whenever you find a sequence, here again 1 0 2 0 4 0 8 0 16 0. Did you see that geometric thing repeats, as well as 0 is being placed in between each of its number, like 2 power 0 onwards, you can see there. Yeah, non-zero numbers are geometric sequence, that is 2 power n with interspread with zeros. 3 6 12 24 48 96 192. How about this? Did you find the relation there? Right, each term is twice the previous geometric progression, that is 3 times 2 power n minus 1. Yes, likewise you can have more sequences and you can try to find the relation in determining the formula. So here each term is 7 less than the previous term. So A sub n is 22 minus 7 times n. Here 3, 5, 8, 12, 17, 23. How about this sequence? Did you find some relation that you can develop the formula there? The difference between successive terms increases by 1 each time. So you can see the differences there. 3, then you have 5. So the difference is 1. Then you have 5, then you have 8. Yeah, so you can see that we are seeing a sequence where A1 or A sub 1 is 3 and A sub n is A n minus 1 plus n. Or you can see A sub n equals n times n plus 1 by 2 plus 2. This is another way of showing it. 2, 16, 54, 128, 250. How about this sequence? Well, then each term is twice the cube of n. So then you can see the formula A sub n is 2 times n cube. Right. Then you have 2, 3, 7, 25, 121, 721, 5041 and so on. How about this one? Here each successive term is about n times the previous. So that's A sub n is n factorial plus 1. Or you can see A sub n is n, that is A sub n minus 1 times n. I mean, here what you have is, this is a simple other solution that you can think of, that is A sub n equals A sub n minus 1 times n minus n plus 1. You can try this out as well. Or you can go ahead and see this online resource page where you can find more integer sequences, just for your reference. Let's see some of the useful sequences that you have in hand. N square, n cube, n power 4, 2 power n, 3 power n, n factorial. Yes, these are some of the useful things. As we talk about the sequence, of course the summation is one way in which you can express the formula of a sequence. And in fact you can also see further on this how you can relate the sequence as well as how you can accommodate the whole structure. Say for example, let's see the notions that is used for summation here. So summation is just like a loop, as you can see here, int sum equals 0, and for integer I equals m, and that is integer j equals m, and j is less than or equal to n, j plus plus, and it repeats there in the for loop until j is less than or equal to n. The same way you have the summation in which we have to add up all those numbers from j equals m till j is less than or equal to n. We are going to see this loop. So this is the index of summation where j equals m, where we had that, and then you have the upper limit which is j is less than or equal to n. So this arrow is supposed to go here, that is the index of the summation, whereas it can go until it reaches n. Until that time it goes to add all those things, that is a of j, that is the lower limit that is starts with m. Evaluating the sequence, as you can see here, we have the summation k equals 1 till 5, k plus 1. So when you put the values of k equals 1, 2, 3, 4, 5, you get this value, summation, summing up. Again, when you put the value for j equals 0 to 4, you get this value to be 11. Again, when I is 0 to 10, I is 1 to 10, we have 30. J equal to 0 till 8, then again you have 5, 1, 1. Note that each term except the first and last is cancelled by one another. So you can check it out when it's going to be as 0. Again, let's see some more points. Let S equals 1, 3, 5, 7, and let's say you have summation J is an element of S, and you have the summation of J there. So you can see here, you can add up all these elements because J is an element of S. So S has 1, 3, 5, 7. So you are going to add all those stuff in that summation. Again, here you have J is an element of S, that is 1, 3, 5, 7. But here you are having J as J square. So you are going to square it off. Finally, you have J as 1 by J. So you are going to have to add up all these ratios there. J is just 1 there. Well, let's see more on this series of geometric sequences that you have in hand. So here we have a sequence in which you have some conditions given, where summation J equals 0 to n, so it can go until n. If r is equal to 1, you have this condition, and if r is not equal to 1, you have this condition. So under this given condition, you can perform your task. So for example, here you are given with summation J equals 0 till 10, 2 power n. So there you are taking up these values and you are trying to find the solution there. Let's see how to have a proof. If r is 1, you are going to use this thing, this form. So if r is 1, then summation S equals summation of J equals 0 to n, A equals n plus 1 times A. So that's what given, n plus 1 plus n plus 1 times A. So with that regard, you are going to rearrange the structure, and then you are trying to see what would be the value of this whole sequence, and you are trying to rearrange things. As you try to rearrange things, J equals 0 to n, and you are going to start from 1 there. So since you are starting from 1, you are taking this 1 outside. So that's where this point is going out. It's here 0 and it's plus 1. So now we are starting from 1, that's why you are removing that part there. So as you progress through this, you are going to include that information, and you are going to add this one part over there, and you are going to proceed further down, and that's your solution that you have. So as you can look back this proof along with this given part, you will see how things would work out. So this is for the other one that you had, r is not equal to 1 there. So here's an explanation of double summation. So when you have double summation, it's like double loops that you have in hand. So here's an example that defines the double loops that you have there, and let's see some useful formulas for summations. For summation of k equals 1 till n times k equals n into n plus 1 by 2. And there are a few more points that you can think about as we talk about the sets. We talked about cardinality. So for finite sets, cardinality is the number of elements in the set. Likewise, for finite and infinite set, two sets A and B have the same cardinality if there is one-to-one correspondence from A to B. So for example, if on a finite set, let's say we have S and T as two sets given here, where S equals 1, 2, 3, 4, 5 and T is A, B, C, D, E. So you have one-to-one correspondence for S and T. For example, 1 is A and 2 is B, 3 is C, and so on. And for example, infinite set, say S equals Z plus, which is like all the positive integers, and t is equals for all x such that x is equal to 2k, and k is an element of positive integers. So that's again having a one-to-one correspondence, but it goes on and on and on. It's like an infinite set. Yes, you are trying to map here and see that goes on. So this symbol here indicates not the biconditional but as one-to-one correspondence. So this is one more definition about the countability of infinite elements. For example, it's not easy for us to prove that, for example, the rational, irrational numbers, integers, even the prime numbers is countable or not. Yes, there are a lot of uncountable infinite elements can be listed. So we should be cautious as we deal with all different numbers, for example, even real numbers. So today we talked about different aspects of sets. The one aspect is the sequence, especially sequence, right? We have talked about sets, and now we can see the difference between sets and a sequence. Sequence is an ordered list, unlike the set, and sequence can have duplicate elements, unlike the sets. Whereas sequence is quite unique, as you see that there are a lot of sequences found in the nature, including the Fibonacci sequence. In fact, there are other sequences with respect to the so-called silver ratio, the copper ratio, and so on. But we talked about golden ratio today. And moreover, you know how to come up with a formula for a given sequence. When you have a sequence, you should know how to come up with a formula, or you should be able to develop a formula for any sequences. And basically we also talked about summations and how the summations can be proved or disproved. I like to give you some more information as you discuss with our assignments and homeworks. I hope to see you there and try to discuss with you about different topics that are related to sequences, and I hope you can do some work and see by yourself whether you would be able to solve some problems that are related to sequence. We are not yet finished yet in this series of mathematical induction, because in our next part we are going to discuss about strong and weak induction. Until then, goodbye.